Hi, I'm Shintaro Ishikawa from Keio University. Let me give a presentation about our study. The title is Target-Dependent Uniter, a transformer-based multimodal language comprehension model for domestic service robots. First, I share the overview. We propose target-dependent uniter for multimodal language understanding for a pattern interaction task. It models relationships between interaction and objects and image. As a result of the experiment, it outperformed the baseline method in terms of classification accuracy on two standard datasets. Next, I'm going to talk about the background of our study. In our aging society, there is an increasing need for daily care and support. Domestic service robots are receiving increased attention because they are able to physically assist people with disabilities and expected to overcome the shortage of home care workers. Our motivation is that it is convenient for users to interact with robots naturally through language. For example, when a user says, "We'll get the bottle on the table," it is desirable for robots to comprehend the interaction and look over the desk and find the bottle and recognize it as the target object and bring it to the user. However, it is challenging to identify target object from interaction. For robots, it is often difficult to find target object when the scene includes multiple candidates. In domestic environment, there are a lot of objects in each room. When looking for the object specified by the user's interaction, robots can be confused by similar objects. Human interactions often contain referring expressions to select a specific one from multiple candidates. If robots cannot understand those referring expressions, identifying a target object is very difficult. So the requisite is understanding of relationships between objects and image. Our target task is defined as multimodal language understanding for pattern interactions, MLUFI for short. We think MLUFI is a part of vision and language field. Related to vision and language, many methods are proposed for learning general representations. Billboard and UNITER are a similar model in that they acquire representations from instructions and images with transformer attention mechanism. But the former uses two separate transformers, and the latter uses a single transformer. Villa is also a vision and language model. However, it is unique in that it introduces adversarial training in the transformer structure and adds perturbations to embedding space to learn vision and language representations. Regarding to MLUFI, Hattori proposed a method for object picking task. MTCM identifies target object from instruction and whole image, and it was extended to MTCM-AB by introducing attention branch networks. However, those existing methods show insufficient performance. These are problem statements. The target task is multimodal language understanding for pattern interactions. The purpose is to identify target object from interaction and image. The inputs are interaction, candidate region, and detected regions. And the output is a predicted probability that candidate region is correct. Let me give you an example. Look at the right situation. A robot is given an instruction, pick up the empty bottle on the shelf, and objects enclosed by blue or green rectangles. Robot is expected to predict the probability that the bottle with green rectangle are correct target object. We propose target-dependent UNITER, which is an extension of UNITER framework to MLU-FY task. We introduce our new architecture for handling candidate objects, which enable us to judge whether it is target object or not. Next, I'm going to talk about 3 modules which compose our method. The first module is text embedder. It embeds instruction and consists of 2 embedding layers and 1 layer normalization. It takes 2 inputs. The first is xinst, which is 1 hot vector set representing each token of instruction. We tokenize instruction using word pace and convert it into a token sequence. The second input is xpos, which is 1 hot vector set representing each token's position of instruction. The second module is image embedder. It embeds candidate region and detected regions and consists of 2 fully connected layers and 1 layer normalization. And it takes 4 inputs. XZ is the feature vectors of all detected regions extracted from image. And XCAN is selected from XZ. As a pre-processing, we use faster RCNN to extract feature vectors from image. And XZ log is the location feature vectors of all detected regions. And XCAN log is selected from XZ log. We use 7-dimensional vector as location features, which are composed of normalized left, top, right, bottom coordinates, and width, height, and area of bounding boxes. The third module is multi-layer transformer. It learns relationships between instruction and image. It consists of several transformer blocks, and each block is composed by 6 layers shown in the right figure. In multi-head attention layer, we generate queries, keys, and values from the input A trans and calculate attention score as a temp using those 3 elements. Look at the left image. We can visualize how the model attends each object like this using the attention score and check the inner working of the model. Further analysis will be discussed in the experiment section. In the experiment, we evaluated our method on 2 datasets. Both datasets consist of images and a set of instructions. The first is PFN pick. A sample of PFN pick is shown on the left side. And the second dataset is WRS-UniOrt. This is a simulation-based dataset which we built in this study. The images were collected in the standard simulator of World Robot Summit Partner Robot Challenge by domestic service robots. A sample of WRS-UniOrt is shown on the right side. These are quantitative results. In our method, we propose 2 conditions. The first is all regions, where we input all the detected regions. The second is proximal regions only, where we select half of detected regions in the proximity of the target region. The table shows the results. It indicates that both of our methods outperform the baseline method in terms of binary accuracy. In addition, our method with proximal regions only achieved the highest score, which means that limiting the number of regions are effective to performance. Next, let me share success samples. In the images, blue boxes denote candidate regions, and green boxes denote ground truth, that is, target regions. Regarding to the left sample, the candidate region represents almost the same region as ground truth, and the output is nearly 1, which means the model correctly identified candidate object as target 1. Regarding to the right sample, the candidate region represents a different region from ground truth, and the output is nearly 0, which means the model correctly identified candidate object as a different object from target 1. These are attention visualization. First, look at the linguistic attention. The model especially attends the word grain container, which represents target object. It also attends the words next to and bottle, which compose the referring expressions. Next, look at the visual attention. Regions in proximity to target object are attended. And in contrast, for regions from the target object are not so attended. Next, let me share failure samples. Regarding to the left sample, the candidate region represents a different region from ground truth, but the output is nearly 1, which means the model mistakenly identified the candidate object as the target 1. I consider the model failed to predict because the candidate region contains many pixels that do not relate to the candidate object. Regarding to the right sample, the model mistakenly identifies the candidate object as the target 1 as well. The reason is the candidate region is too small to extract fine-grained features. These are the results of ablation studies. We set 4 ablation conditions. The first is without FRCNN fine-tuning, where faster RCNN is not fine-tuned on each dataset. The second is late fusion, where candidate region and other inputs are handled by separate networks. Specifically, the candidate region is not processed by a multi-layer transformer, as shown in the left figure. The third condition is few regions, where the number of detected regions is randomly reduced by half. And the fourth condition is without UNITER pre-training, where pre-training proposed in UNITER is removed. The table shows the results. It indicates that our full method achieved the higher score than any other condition, which means each component contributes to performance. So let me conclude my presentation. We proposed target-dependent UNITER for multimodal language understanding for pattern interactions task. And it models relationships between interaction and objects and image. As a result of experiments, it outperformed the baseline method in terms of classification accuracy on 2 standard datasets. Thank you.